So last time around, we basically finished off the topic of monads, which is the first half of the Advanced Functional Programming course. So what we're going to be doing today is a couple of things. We're going to kick things off with one final small exercise on monads, because this actually brings out an aspect that we haven't talked about so far. And then we're going to start the second topic of the course, the final topic of the course, which is reasoning about programs. So to kick things off today, we're going to do a simple exercise. And if you're reading along in the book, it's actually exercise 7 from chapter 12 on monads and more. And what we're going to be doing is thinking about a data type of expressions which are built up from variables. And in order to be flexible, we're going to consider variables of some arbitrary type A. So what we're going to have here is a data type declaration. So I'm defining a new data type called expr for expressions, and it's going to contain variables of some arbitrary type A, so make that a parameter of the type, and then there are going to be three ways that you can form an expression. So an expression can either be a variable which has a parameter of type A, or it can simply be a value which we'll make simple, we'll simply say is an integer, or we can have the addition of two sub-expressions, and these will be both of type expr A as well. Okay, so this is the data type that we're going to be working with. So we have expressions that contain variables of type A, and these are either variables of type A or values which are integers, or the addition of two sub-expressions of the same type. So just to make sure that everyone is happy with the data type, let's have a simple example of this. So suppose we wanted to represent the expression x plus 1 as a value in the expression data type. So how could we do this? Well, there's various different ways that we could do this, because the data type is flexible. You have different kinds of variable types that you can pass in as parameters. So here's one possible way which I could represent this expression. I could say it's an addition, and I have the variable character x, and I have the value 1, and this would be of type expression of char. And it's an expression of char because when I have the variable here, notice that I have a single character x here representing the variable. So that tells me that in the end, this is going to be an expression where the variables are characters. But this is not the only way which I could represent this particular expression, x plus 1. There's many other ways I could do it too. So for example, I could have addition, and I could have the variable, and this time I could make it a string, so double quotes rather than single quotes, and the value 1 just stays the same. And this time around, this would be an expression whose variables are strings. And again, this is because this time the variable is a string in double quotes, so we have an expression whose variables are strings. And of course, we could imagine representing the variable in many different kinds of ways. So in general, there may be many more other ways that we could represent this particular expression x plus 1. Okay, so the name of the game here is we have this data type, which is flexible in that it allows expressions to be built up from variables of an arbitrary type A. And this gives us the flexibility to do things like this here. If we wanted to represent something like x plus 1, we could do it in multiple ways by representing the variables in different ways. So the expression type is a parameterized type. So at this point in the course, it's very natural to think, can we actually make it into a monad? Assuming, of course, that we had already made it into a functor and an applicative functor, which I'll leave as an exercise to you. So let's work out how we could make this type into a monad, and then what this actually means in practice. So we're going to be making, as usual, a simple instance declaration. So we're going to write instance, and we want to make a monad. And the parameterized type we want to make into a monad is the expression data type. So all we need to do is the usual game. We need to define a return operator. So we can write down the type of that. So return is going to go from, as usual, A into M of A, but here M is the expression data type. And then we think, how do we actually define the return function? So what is return of X? So in this case, this is extremely easy. If we're given a value x of type A, and we want to build an expression whose variables have type A, then that's very easy because we already have a variable of type A, that's x. So all we need to do here to get something which is type correct is simply return var of x, and this will have the right type. So this is very easy. So let me make a bit more space here now. Let me knob this one out, and we're going to now think about how do we define the bind operator. So as usual, we write down the type of the bind, and it's exactly the same as we've seen many times before. So we take an m of a, where m is expr, and then we take an a to mb, so that's going to be a to expr b, and then we're going to give back an expr of b. And we're going to do it by case analysis on the expression argument here. So we're going to have 3 cases. So let's consider the first case. We're going to have a variable v, and that's going to be feeding into a function f. And all we need to do now is kind of track through the types and think what is a reasonable definition to make which is going to end up being type correct. So as usual, what we can do is kind of write down all the types and see what happens. So let's start on the left hand side. So the variable v is going to have type A. And then when we apply the var constructor to it, that's going to build us an expression of type A. Then we can think, well, what is the type of f? Well, we can just read that off from up here. This is the second parameter, so that's going to be the type of f. So I can copy this down as well. F is going to go from A into expression of B. And then when we apply the bind here, we know what the bind does. It takes an expression of A and an A to expression of B, and it's going to combine them to give us an expression of type B. So if we kind of complete the picture on the left hand side, this is all got type expr of B. So nice and easy. So now we can think, well, what are we actually going to write on the right hand side here? Well, it has to be something of type expr of B because we have an equality here. So equality always goes between the same types. So how can we build something of type expr B given what we have got? So we can think, what have we actually got on the left hand side? Well, we have a value v, which is of type A, and we have a function f, which is of type A to expr B. So if we simply apply the function to the variable v, that will give us something of type expr b. So a nice, easy definition. So if we simply then apply the function f to the value v, that will be something of the right type. So now we have completed this case. So let's get rid of these types here, and then we'll think about the other 2 cases as well. So the next case now is we're going to think what happens when you feed a value n, can't spell today, a value n feeding into the function f. And again, we just track through the types and we'll figure out what is the right thing to do on type grounds. So we can look at the right hand side. What is the type of value of n? Well, we can simply read this off. It's an expression of type A. So that's very easy. So down here, this is simply an expr of A. And then again, the function f, we can read that off from the definition. It's an A to an expr B. So that's very easy to complete as well. So that's an A to expr B. And then as before, when we apply one to the other with the bind operator sitting here in the middle, then we're simply going to get back an expression of type B. Okay, so we get an expr B back here. So nice and easy again. So then we need to think, well, what could we actually write on the right hand side here? Well, we've got a function, so we could think about applying it. So if we look at the function here, f, it goes from A to expr B. So if we had an A, we could apply it to get an expr B, but this time around we don't have one. I mean, this thing here is an integer, whereas up here, this was a value of type A. So we can't actually apply the function in this case because we don't have a value of type A. So then we can think, well, what can we actually do to proceed? Well, the trick this time is we'll actually just return val of n, because val of n has type expr of A for any A. So in this case, on the right hand side, this could also have type expr of B. Okay, so this is a bit more of a tricky case. You need to think about this one a little bit. So then let's come on to the final case, which is what's going to happen when you feed an addition into a function. So we're going to feed an addition, add of xy, and that's going to be feeding into a function f, and what do we do? So again, let's think about the types. So on the left-hand side, this whole thing is of type expr of a, and because of the add constructor, we then know that the types of x and y are also expr of a as well. So I can write those down. So this and this both have type expr of a. That's just simply reading off from the type. The function f is as before. Well, actually, let's just complete this on the left-hand side. This means if we've got two arguments, x and y, which both have type expr a, then when we put them together with the add constructor, then on the left-hand side, we're also going to have an expr of a. Okay. Then the function f, that's just stayed the same type as it's always been. F has type a to expr b. So we can copy that down as well. This is, let me get this in the right place, a to expr of b. And then same game again, as we've done 3 times now. When we apply the bind for something of type expr a to expr b, then in the end, what we're going to get, right down the bottom, it actually does fit on the slide, which is good, is we're going to get an expr b down here. So then we need to think about the right-hand side, and again, we're looking to build something of type expr b. So I'll write down the answer this time, and then we can think, why is this actually correct? So what I'm going to do here is I'm going to have an add, and then I'm going to recursively feed x into f and y into f as well. So why is this the right thing to do on type grounds? So let's have a look first of all at these 2 parts here, the parameters to the addition. So what we're doing in the first case is we're feeding x into f. So we can think what actually is going to be the type of this. Well, x has type over here, it's an expr of a, and f goes from a to expr of b. So when we feed one into the other, we're going to get an expr of b. And actually, it's going to be exactly the same for y. Y has the same type as x, and when we feed that into f, we're also going to get an expression of type b. So what we get on both sides here is these are expressions of type b. And then when we apply overall, when we apply the add constructor to both of these things, if add takes 2 expressions of type b, which we have, then the whole thing is going to be an expression of type b. So just to complete the picture down here, we have an expression of type b. So again, it's not much of a spectator sport when you watch someone doing this kind of thing, but this is definitely the kind of stuff that you need to be able to do for yourself. I could easily ask a question about this in the Advanced Functional Programming exam. So make sure if I give you a simple data type, like the expression data type, and ask you to make it into an instance of the monad class, that you can track through the types like this and come up with this kind of definition for the return and the bind operator. So now that we've made the expr type into a monad, the question is, well, what does this actually mean? What does it actually do? And in particular, what is the bind operator actually achieving for us? And actually, what I want to show you now, by means of a simple example, is that it implements a very common idea in computer science, which is the idea of substitution. So let me give you a simple example of a substitution. So suppose I define the function f, which is going to substitute for the variables x and the variable y. And here the variables are simply going to be characters. So I could decide, for example, I want the variable x to be just 1 plus 2. So I could define the substitution to say if you substitute for x, you get 1 plus 2 written in the expr type. And what am I going to do with y? Well, let's just say maybe that's going to be substituted by the value 3. So this is a simple substitution, a function f, which tells me how to substitute for x. So in this case, x is going to be 1 plus 2, and y is simply going to be 3. If we work out the type for this, what the type is f is a function. It takes a character as input, and it builds you an expression. And actually, I haven't used any variables on the right-hand side here, so this is going to be completely polymorphic. This will build me an expression where I don't actually care what type of variables I have anymore, because I don't actually have any variables in the expression. So there's an example substitution. What could we actually do with it? Well, we could apply it by using the bind operator. So an example would be if I take an expression which contains the variables x and y. So if I had the variable x added together with the variable y, and I want to apply the substitution, then I simply bind into the function f. So this is x plus y written as a value in the expression data type, and I'm feeding it into the substitution called f, and what we'll see is that this is actually going to substitute these two expressions in for x and y. So if you actually track through the details and you type this in, what you'll find is that you get exactly what you would expect. So you get the same expression, but now x has been replaced by add of val 1 and val 2. So x has been replaced by 1 plus 2, and the y has been replaced by 3. So again, what we see is you take an expression which contains variables, you feed it in using the bind operator to some function f, which is going to be a little substitution, and then what we see concretely is that the variable x has been replaced by 1 plus 2, and the variable y has been replaced by the value 3. So what we see here is that the bind operator for this expression data type implements the idea of substitution. And a couple of little final comments I'd like to make here. Monads are basically about programming with effects in a language like Haskell, but this example is a nice one because the idea of substitution and these expression data types, it's not really clear to me how these are related to effects. So maybe this is a kind of non-effectful example of a monad in Haskell. So that's something which is interesting to think about. And the second thing which is maybe interesting to think about is what do the monad laws actually mean for this particular example? And if you work through the details, you'll find that they're actually very common and very useful properties of substitution. So what we're going to be doing in the second part of the Advanced Functional Programming course is thinking about a new topic, and the new topic is reasoning about programs. And we're going to be looking at three particular things. So the first thing we're going to be thinking about is how to do proofs about programs. So when you're at school, you learn how to do some simple proofs about numbers, but in this course, you're going to learn how to do some simple proofs about programs, and in particular, Haskell programs. And the emphasis here is going to be on the process. We're not going to be doing particularly complicated proofs, but we're going to be very careful about the process which we're actually using to construct those proofs. And this is in sharp contrast to many of the courses which people teach about reasoning about programs. Often those are taught by very experienced people, but they don't kind of tell you what the rules of the game are because they're so familiar to them that they don't actually kind of see the basic rules anymore, or some of the basic rules. So what I want to try and do is be completely honest and show you from the ground up how to do kind of simple proofs about programs with the emphasis on the process. The second thing we're going to be thinking about is how to improve program efficiency. So if you did the introductory Haskell course with me in the first year in Nottingham, one of the things which I said to you is don't worry about program efficiency, just write clear, concise and correct code and let the compiler worry about efficiency. But sometimes, of course, you do need to worry about efficiency. So what we're going to be thinking about is how to improve program efficiency in a language such as Haskell. And we're going to be learning about techniques such as accumulation, which we'll see actually relates to the first point about how to do proofs about programs. And then to wrap things up, what we're going to be doing is looking at a simple case study. We're going to be proving that a compiler is correct for a very, very simple language. And that will kind of bring together everything that we learn about in the second half of the course. If you're reading along in the book, this is chapter 16 we're going through here, which is reasoning about programs. So before we start thinking about reasoning about Haskell programs, I want to go right back to basics and go back to the kind of simple equational reasoning that you learn at high school. So at school, you learn some basic algebraic properties of numbers, and I'm going to give you 4 examples of simple algebraic properties that you'll all be familiar with. So the first one is if you have any 2 numbers x and y and you multiply them together, that will be the same thing as multiplying them in the opposite order. So x times y is the same as y times x, and this is what's known as the commutativity of multiplication. And obviously here I'm writing multiplication just by writing things next to each other. So here's another property you learn in school. You learn the x plus y plus z. So 3 numbers added together, but bracketed to the right. That's the same thing as bracketing them to the left. So if you add 3 numbers x, y, and z, it doesn't matter whether you bracket them to the right or to the left. And this is called the associativity property of addition. So I'm going to give you 2 more properties, and these are distributivity properties. So the first one, if you take x and you multiply it by y plus z, then you can actually distribute the multiplication through on the left, and you can get x times y plus x times z. So that's a simple distributivity property, and you have one the other way around as well. If you take x plus y times z on the right, then you can distribute through the multiplication on the right, and you'll get exactly what you expect. You get x times z plus y times z. And again, this is a simple distributivity property. So these are the kind of algebraic properties of numbers that you learn at school. So what do you do with these at school? Well, you use them to reason about simple numeric expressions. So here is a very familiar equality that you learn about at school. If you have x plus a times x plus b, then you can multiply out the brackets. You all know how to do this from school, and that's the same thing as x squared plus a plus b times x plus ab. Okay, so let me put this in a box here because we're going to be thinking about this. This is a simple arithmetic equation or equation that you learn about at school. So what I want to think about is how can you use these 4 simple algebraic properties to prove that this equation is actually true using equational reasoning. So that's what we're going to be thinking about now. So what we're going to do now is a little calculation to show that this equation is actually true. So what we're going to do is start with the left-hand side, which is x plus a times x plus b, and in a sequence of simple equational reasoning steps, hopefully we're going to end up with the right-hand side. So I'm going to do about 5 steps here, but I'm actually going to cheat, and it's a little exercise for you to try and spot how I'm cheating before I explain this after we do the calculation. So looking at this expression, what could we do with it? Well, we've got something multiplied by an addition. So we could apply our left distributivity property and distribute through that addition. So that's the first thing we're going to do. So we're going to get x plus a times x plus a times b. So I've simply exploited the left distributivity property here. So then what I could do, well, I could apply the right distributivity property. Here I have an addition times something, and here I have an addition times something. So if I have the right distributivity property at my disposal, I could multiply out the brackets, and I'll get x times x plus a times x, and then on the other side, I'm going to get x times b plus a times b. So what can I do now? Well, I'm going to make one tiny simplification immediately, which is not where I'm cheating, which is I'm going to simply replace x times x by x squared, because that's just another way of writing x times x. So I can write immediately x squared in here. So then what I'm going to do? Well, actually what I'm going to do now is I'm going to exploit the commutativity of multiplication. So x times b is the same as b times x. So I can do that step as well. So I just copy everything else down, a times x. So here I'm going to get b times x, and then a times b. And why was this a good thing to do? Well, it was a good thing to do because now I have something where I can apply one of my distributivity properties. If I apply the right distributivity property here, I can simplify a times x plus b times x to something. So let me write down what we're going to get here. So if I apply the right distributivity property, I can factor out a plus b times x, and then I'm going to get a b. So this completes the calculation, and what we have shown is that this thing here equals this thing here by a simple sequence of equational reasoning steps, and this is precisely what we needed to show. And now you might be thinking, well, where did I actually cheat? Well, where I cheated is I implicitly exploited the associativity of addition. So how did I exploit this? Well, if you look here and here, when I multiplied out the brackets, I didn't put any brackets in this second line here. But I really should have done. So I should really have put brackets, let me do this in red, I should have put brackets here and brackets here. But I didn't actually need to because addition is associative. And this is important here that I actually do think about the brackets, because when I come to do the distributivity property in the end, so when I factorized this and got a plus b times x, I was assuming that this part here was grouped like this, so the brackets were here. So what I'm implicitly doing is, in moving from this step to this step, I was also implicitly regrouping the addition. But I didn't tell you that, and that's because implicitly, when we're doing calculations, we usually exploit things like associativity properties without actually mentioning them. So this is very common, but again, this is the kind of thing that people often don't show you when they're teaching you about simple equational reasoning. So just be aware of these kind of things. So just before we move on, you might think, well, why are algebraic properties such as these things actually interesting in computer science? Because, I mean, you're a computer scientist, you're mathematicians. Why should you care about, for example, that algebraic property if you're a computer scientist? And actually, there's an efficiency concern here as well. If you look at the left-hand side of this distributivity property, there are two arithmetic operators. There's one multiplication and one addition. Whereas on this side, which is precisely equivalent, there are two multiplications and one addition. So this distributivity property might be an optimization which you could apply in your program. And in particular, if you saw something like x times y plus x times z, that uses three arithmetic operations, but by distributivity, you could rewrite it like this, and that only uses two. So arithmetic or even simple algebraic properties of numbers might be interesting to you as a computer scientist because they may give you efficiency gains. So now that we've had a quick refresher on the idea of equational reasoning, let's think about how we could apply this idea to reasoning about Haskell programs. So let me give you a simple definition. So we're going to define a function called double. And double takes an integer and gives you back an integer. And it's a simple one-line definition. Double of x equals x plus x. So just a simple one-line function definition. However, we can also view this function definition as a property that we can use in equational reasoning. And we can use it in two ways, one of which is very familiar to you and one of which is probably not so familiar. So the familiar one is we can use it in a left to right direction by simply applying the function. And the idea here is if I give you any integer expression x, then the expression double of x can be freely replaced by the expression x plus x. So this is just the standard idea of running a function from left to right by applying it. However, in a language like Haskell, where equals actually properly means mathematical equality, you can also run your functions backwards. And what this means is that whenever you have any integer expression x, the expression x plus x can be freely replaced by the expression double of x. So when you're doing equational reasoning, you can freely replace the left-hand side by the right-hand side, or if you wished, you could freely replace the right-hand side by the left-hand side. So the terminology is that functions can be applied from left to right, or they can be unapplied from right to left when you're doing equational reasoning. But there's one little caveat, and the caveat is that you need to be a bit careful when you have definitions using multiple equations. So let me give you a simple example of this. So I could define a little function called is0, and it's going to take an integer as its parameter and give me back true or false, depending on whether the integer is 0 or not. And one way to define this is I could use pattern matching with two equations. So I could say is0 of 0 is true, and is0 of anything else is false. So a nice simple two-line function definition for the is0 function. But there's a little caveat here, and the caveat is if you wanted to use these two equations, this one and this one, in equational reasoning, the first one can be used freely in both directions, but the second one cannot. So you can ask yourself, why not? So let me give you a simple concrete example, first of all, of what the problem is here. What I'm going to show you is that false equals true by using equational reasoning with these two equations. So I'll start off on the right-hand side here. I want to show that false equals true by equational reasoning. So I'm going to actually do two steps here, and I'm going to end up down here with true. So how am I going to show you that false is true? Well, first of all, I'm going to unapply the definition here, which says false can be freely replaced by is0 of n. So I'm going to choose to replace it by is0 of 0. So I could replace that by is0 of 0. By unapplying the function definition. And then, of course, what I'm going to do is I'm going to take that and say, well, I could apply the function definition here and simply get back true. So if I do that, I'm going to get back true. So what I've proven here for you is that false equals true, and that's an inconsistency. If you can ever prove that false equals true, your whole kind of reasoning system collapses and you can actually prove anything. So this is actually not a valid proof here, and it's not a valid proof because I cannot simply apply the second equation in any way that I like. And it's because the order of equations matters. So if you think about this definition here, the first equation says is0 of the number 0 is true, and the second equation actually says is0 for any number n that is not 0 is false. So if I wanted to use the second equation here, I can apply it in the left to right direction, provided that the number n is not 0, because the 0 case would already have been dealt with up here. And similarly, in the right to left direction, if I wanted to replace false by is0 of n, I can only replace it by n, where n is not 0. Okay? So you have to be a bit careful when you're reasoning about multiple equations. As a result of this, it's actually preferable to define functions without relying on the order of equations. Okay, so what I would actually prefer to do in Haskell with this one here is actually modify the definition a little bit. Say is0 of n such that n doesn't equal 0 equals false. Okay, so what I've done here is I've modified the definition and put on an explicit guard here, which makes the implicit constraint that n had better not be 0 in this case explicit. And now you could use these both of these equations in the left to right direction and the right direction and the right to left direction, because the constraint that n is not being 0 is now made explicit in the second equation. If you define your functions like this, where there's no overlap between the different equations, this is called disjoint patterns or non-overlapping patterns. Okay, so this is a terminology. This is a definition here using non-overlapping or disjoint patterns. So just a couple of final notes before we wrap things up today. When you're doing equational reasoning, to simplify the reasoning, it's good practice to use disjoint or non-overlapping patterns whenever possible. So this definition here doesn't rely on the top to bottom matching of equations. It's just completely valid in any order that you consider it. And actually, second point to note is most library functions are defined using disjoint or non-overlapping patterns. So that's it for today. We've had a simple kind of introduction to the idea of equational reasoning, and we've started to think about equational reasoning in Haskell. And next time around, we'll start to do some more sophisticated reasoning. So see you again next time.